Computer Science and Engineering at the IIT Bhubaneswar to the stage. Please join me in welcoming her to share her insights on future of machine learning and its application.
A very good morning, everyone. Thanks a lot for having me over here, and it was a wonderful opportunity for networking, get to know each one of you and what you are working on. So, is my voice audible to you?
Yes.
So, we'll start with discussing what is AI and what is the need of, or what is the role of revamping the AI infrastructure. What are the challenges that AI poses given the massive scale and data sizes? And then we will go on into a little bit of energy efficiency work that we have been focusing on recently. And feel free to stop me anytime you have questions, and I'll get started. Okay. So let's start with discussing. Let's start with discussing the fundamental question. Let's say, what is a cat? How are you going to define what is a cat? So in the traditional programming, we would be defining a cat and that what is the type of my cat, it's an animal. We'll have a switch case statement which will define different features of my cat. So one is the type is animal, number of legs it has is 4, the ears it has is 2, fur, yes it has, and what are likes, dislikes, etc. Moving forward, in 2012, we had the wave of neural networks where we used the supervised learning. So in the supervised learning, in the data set, we are giving a bunch of images and we are labeling each image. This is a cat, this is not a cat, and it could have a mix of both cat and not cat images. And once the model is trained, while testing it, we can give it the picture of a cat in another pose, which is a sleeping pose, and it should be able to correctly identify that this is a picture of a cat. Classification problem with supervised learning. Now, since 2022 era onwards, we had generative language models like Lambda, PLM, GPT, etc. And so here, instead of giving or annotating each images that we are giving, that this is a picture of a cat, this is not a cat, what we are going to do, we are going to say, go through this pile of books, learn it yourself, not just about cats, but about other million concepts that are in those pile of books. And once the model has learned, when we are going to test it, now we are going to ask the question, what is a cat? Then it's the chatbot or the summarization tool, depending on the task, it's going to tell us a cat is a, depending on whatever it has learned from those pile of books, it is going to give us the results based on that. So now we discussed language model. So if I ask this question to myself that what is a language model now? So well, language model is something that takes an input as a prompt or a question, and the output that we expect is again a text-based response. Whatever happens in the middle is the processing, in which it analyzes the input, builds a model, and then generates a response based on all the learned parameters that it has. And the language model fits into the area of like deep learning, and which fits into a subset of machine learning. Now let's see and test our understanding of the language models using this example, where the question is, or the use case is to predict the next word in the sequence. We have a sentence. We have to fill in the blanks or predict the next word that is going to come. Let's say the question is, last night I was reading Harry Potter and the, so you have to predict the next word in the sentence. What will be your answer? Forget about language models, machine. Let's assume that like I'm asking this to a human being. So what will be the answer that I'm going to expect?
Power went off.
Sorry?
Power went off.
Okay, that's interesting. It's an exception, but that's not typically how all the like everyone is going to answer. So what are the different flavors of answer that I can expect today?
Order of minutes.
Order of Phoenix, okay. So which means that when we hear the word Harry Potter, the context that comes to our mind, it's a fictional character, probably the central character of that fiction. And the basically probably is one of the books, name of one of the books, Harry Potter and the X. So we have to predict what is the X, and X should be probably within the names of the books. We can get the value of X from that. That's exactly how the machine also thinks. So these are the names of the novels involving Harry Potter as their central character. So which means like it has Goblet of Fire, the Chamber of Secrets, etc., etc. And then we are going to associate after the word Harry Potter occurred, what is the probability of occurrence of the word philosophers or sorcerers or prisoners or goblets after that specific word. Based on those probability of occurrence, we are going to give it a score or a value, and we are going to fit in the highest probability as the next predicted word. In this case, it's philosophers. So that's what the machine did, large language model. Now, if I twist the question a little bit, I add a concept or a context saying that, remember, I live in New York and I bought my book from United States. What is this additional piece of information, or how is this additional piece of information going to change my answer or my final prediction? So the catch here is, because the word philosopher was not that, like the US audience could not relate to the word philosopher that much, that's why it was renamed and launched as Harry Potter and the Sorcerer's Stone in United States, and all over the world it was launched with the name of Harry Potter and the Philosopher's Stone. And the fact that I am in New York and I bought this book from United States essentially reinforces that probably I might not have read this, I might have read the Sorcerer's Stone. So then it's going to recalculate the probability based on this added context. So in the large language models, context is also very important for us to know. And then after recalculating the probability, the Sorceress has the maximum probability word. So that's going to be the next word in the predicted sequence. Okay, so we got a clear understanding of what language models are and what are the use cases and so on. Now, what is large about my language model, and why should I be concerned, or why is this word large that important? So it's called large because it is trained on massive amount of data. What will happen if you don't train your model with massive amounts of data? What do you lose? Any thoughts? You will have less accuracy, it will be less skewed, and you will have the problem of overfitting. You are going to, like, it's basically memorizing something. If one says 1 multiplied by 2 is 2, you are going to repeat it, then 1 multiplied by 4 if you say, then also you are going to say 2 and so on. So, second, and the other characteristics are, apart from the massive scale, which means it's trained on billions of words, it also relies on unsupervised learning, which means we have lots of raw data without explicit need of labeling. So no human is needed for the labeling purpose. And here we have to utilize deep neural networks with like lots and lots of hidden layers. And so, needless to say, we have been using ChatGPT and the large language models extensively in our day lives. So both the students and the instructors, we use ChatGPT to see what are the different types of questions that we can have, and taking that as a starter, we are trying to build our own thoughts around it and so on. Same with students, like assignment मिल गया, check करो ChatGPT में है या नहीं, and then see what you're getting, and then like you're building your answer on top of that. So there are like the commonly used LLM models are GPT-3, Lambda, BERT. Almost every FANG company is in the AI race, and they have built their own version of the LLMs. So now, if I take a step back and rethink, what are the exact driving forces of my computing? Well, I need faster computing because let's say I'm asking my ChatGPT a question or something to summarize. I don't want to wait for like 15-20 minutes before it gives me the answer. Like everything should be fast, or else like we lose patience, the quality of service will fall down. Next is the algorithm. We want better accuracy, smart algorithms. If let's say my data set has been trained my model has been trained with a specific data set. If I'm adding something new, it should be able to revamp itself. Like I don't have to retrain everything from the scratch. So I need better algorithms. Also, I need more data to avoid the problem of overfitting and accuracy and so on. And at the end of the day, I want a good value for my money, and what lies in the middle is the magic box or my AI infrastructure. How should I make my AI infrastructure that it should be able to process and consume all these three inputs and produce the output that you want? So, from the lens of a computer architect, we can summarize the major challenges in the LLM optimization as memory constraints and management, computational complexity and resource requirement, latency and throughput. Let's start with the memory constraints and management. So when I have a lot of data, I'm talking about trillion parameter sizes. So I need to store it in somewhere, and whenever I'm doing any computation, I should be able to retrieve the data at the fastest rate possible. If that becomes slow, my whole pipeline gets delayed and my overall response time will increase. Next is the computational complexity and resource requirement. When we are moving towards more data and complicated algorithms or better algorithms, my processor should be able to process those. I should have those functional units that is going to understand and do the needed operation. And like second thing is with day-to-day life. So the amount of data that let's say ChatGPT was dealing in 2022, is it the same as the data that it is dealing with in 2024 or 2025? No, the data size is floating up. So accordingly, my underlying infrastructure should be scalable so that I can fit in more and more data, more complicated algorithms, and probably more better models. Last is latency and throughput considerations. So what is latency and what is throughput? Do they mean the same thing, and these are just different synonyms of the same thing, or they are different?
Latency is delay, time taken. Throughput is how much data it can deliver at a particular point of time.
Excellent. So which one do you want? Like, is latency more important or is throughput more important?
Both will be required. Latency should be low and the throughput should be more.
Yes, I want both latency as well as throughput. So latency is, let's say I'm giving an input, after how much time will I expect an output? That's the latency. Throughput is at a given point of time, how much data am I processing? So the CPUs, the traditional CPUs were excellent with latency. They were giving you results within a short span of time. But they were bad with the throughput. At a given point of time, they are processing only less number of data items. But now I have so many billion parameters or words. I can't wait for like 2-3 words to be processed at a given point of time. I want the throughput or the bandwidth to increase like anything. So that is the role of the accelerators. So that's the reason we had need for accelerators in order to support high throughput processing along with low latency processing. So if I summarize the problem that we discussed so far, the problem is we need data and compute requirement for LLM or AI models. So the obvious solutions are we need advancement in the hardware, we want better algorithms and better data sets. Okay, anyone who can recognize the person in this picture? Apologies for a distorted picture, but this was from a real talk. I captured it. So do you know, like, does this person seem familiar to you in any sense? No, so he's not Leonard. So actually, the Hennessy and Patterson, like people in computer science reading computer architecture book, that's the fundamental book Hennessy and Patterson followed all around the world, starting from Harvard University to every university in the whole world. We read that standard book at the undergrad level as well as the postgrad level. So the authors of the book were John Hennessy, who was a faculty in Stanford University, and David Patterson, who was a faculty at the UC Berkeley University. And there was the Turing Award, which was probably the most prestigious award in engineering in 2017. And they repeated their Turing, so because they both are computer scientists, they came to the flagship conference in computer architecture, IACA, hosted in LA in 2018, and that was the lecture. So the main, so they started with what got them the Turing Award, what was their main contribution in the field of computer architecture, systems, processor in general. And then they also hinted at where are we heading next? After 2024, 2025, where are we heading next? What should be the main focus of the computer architects or the systems community in general? So I was lucky enough to attend his talk in person, and that was my the picture I captured. So okay, the data scale and the technology scaling. So many of us like probably have been working on the semiconductor scaling, semiconductor vision and so on. So what does this picture convey? So here I can see that like the orange line from like x-axis I have 2000 to 2020 and like nanometer is from 180 to probably 4 nanometer. What does it represent and why should I should care about this? The nanometer is decreasing, why is that important for me?
After a certain level, you cannot come closer to the atomic.
Yes, so your answer is like why did I stop at here? Why did I not go down? My question was like why do I have to scale down? That was my question.
To fit more power in smaller space.
So if I have like if I reduce the W by L ratio of my transistor, I can fit in more and more transistors into the same chip area, which translates to better performance within the same chip area. Right? So that is why I needed technology scaling. And the another thing that Dennard promised was like the power also increases at a similar rate. So power is probably proportional to how many transistors I will have in a chip area. That was Dennard's law or Dennard scaling. Now this slide basically talks about the roller coaster ride that the processor technology or the processor industry has gone through, starting from 1980 till like 2024. And the major contribution of Hennessy and Patterson that got them Turing Award was this, the RISC processor. So the story started like this. They were young faculties, just like the way we are visiting here in the form of a symposium. So they met in a symposium and then they started scratching their head over the CISC processors. How the instruction sets are getting more complicated and like the architects have to look through the microprocessor things. And then they thought, okay, let's break down the complex instruction into small, like simpler instructions, reduced instruction set computer. What do we gain out of it? Needless to say, initial years, their papers were rejected and criticized like anything. Because it was a new idea, people were not okay with that because when you are increasing the number of instructions, your IPC goes down. And IPC or instructions per cycle is one of the metrics for measuring the processor performance. So if I'm saying my IPC is going down, which means you are coming up with a bad processor, why will I buy that? So nobody bought that idea, obviously. But later on, the massive ramp in like 52% per year, the performance scaling happened because of the RISC processors. They were able to map it to the ARM, Spark, like all those different simpler versions of the processor. And then with that, we also had around 2004 time frame, the number of transistors that were going to fit into the chip area, Moore's law, which promised that okay, every 18 months I'm going to have double the number of transistors in my circuit, actually zeroed down, and that was also backed by Dennard scaling. So Dennard scaling said, you are increasing the number of transistors per chip area, fine, but this is also a promise that your power is not going to run exponentially, it's also going to be proportional. That actually started failing around 2005 time frame, and that is the reason my single processor is not meeting my expectation. I'll have multiple processor on multi-cores. That gave birth to the multi-core era. We had multiple processors and so on. And then when I'm having multiple processors, let's say I'm running a workload. I got 1000 processors to run this workload in parallel. Will I get 1000x speed up? Is that possible? No. So Amdahl's law actually gave a theoretical limit to how much maximum speed up I can expect if I'm parallelizing my workload and I'm having enough, like assuming infinite number of parallel processes. But still there is a theoretical maximum that you can get. Amdahl's law also said that make the common case more faster. If you have an application, 80% of the time you are calling function x, 20% time you are calling function y. Spend time, effort, energy on optimizing the function x, which runs for 80% of the time. That was Amdahl's law. And then he asked the question, what's next? That, I'll ask to the audience, what's next do you foresee in the processor industry? I think Pillai sir also in his talk today mentioned that the AI we are seeing today is because of the infrastructure support. Like if the GPUs or NVIDIA did not keep to the mainstream and did not launch the GPUs that they did, we would not have seen like models like LLMs and ChatGPT, etc. Right? So what next do you foresee? The reason I'm asking this is even though I have some answer, my perspective, This is also an opportunity for me to learn from all the audience, and I don't want to let go of that opportunity. So what next do you foresee is the trend in the processor performance?
3D crosspoint.
3D?
Crosspoint.
3D crosspoint, yes, we have now 3D network on chip, 3D caches, 3D memory so that we can fit in more data. What next?
Quantum processing.
Quantum processors, yes, I really want to see that day where I can test my algorithms on the quantum processor, but I'm still at the classical thing, not gone to the quantum computing yet. So, what next?
Neuromorphic.
Neuromorphic, yes, it's in a way energy efficient and so on. So the answer is to come up with domain-specific architectures. So what does domain-specific architecture mean? Let's say I have autonomous vehicle domain. How do I design a chip for the autonomous vehicle domain? I don't want a chip to do X, Y, Z million things in the world. I don't want a CPU replicated. I want a chip that will do only specific domain. Again, domain is not one application. It's a bunch of applications. Let's say 20 applications. Autonomous car, I'm driving. So the autonomous car should be able to communicate with the other cars driving on the same road. So that is your transmission and receiving application. It should be able to look at the traffic lights and try to make sense out of it. So some computer vision application. It should be able to see the obstacle and stop, brake right in front of it. So these are a bunch of applications taken together, which is defined as a domain. So I want a chip or a processor that should meet the requirements of a chip, which means I do not want 100% functionality, just those specific applications I want to be supported. Also, I want best performance and the lowest energy consumption out of this. So GPUs?
Initial computing was of that nature, and then
We had A6, yes.
x86 had changed it. So we have to go back to get better performance.
Yes. So A6 was also like one application. Here we are talking about a scale of
Yeah.
applications fitted into one domain. So GPUs, the neural processor unit, and programmable network switches are all different categories of examples that we can think of as domain-specific architectures. Now coming up to the question, how has the deep learning hardware evolved over the years? So taking a quick pick, we see that the complexity of the deep learning algorithms, so again on the x-axis I have the years, and on the y-axis the time or the number of days of training that it needs. And then, so this is a picture taken from the NVIDIA. So from 2012 to 2015, we had one trajectory. Something happened in 2017 time frame, and the trajectory is just skyrocketed like anything. What exactly happened in 2017? Anyone? Any thoughts? Processing power has been increasing, but no magic happened in that specific time frame as such. So here I am talking about the deep learning model scaling up.
Attention is what.
Exactly, thank you. Attention is all you need. That was a paper by Google Brain published in NIPS that basically introduced the transformer model. They had an encoder and decoder part, and how you can store the context information for a longer duration of time and so on. And after that, we see that the complexity and everything started increasing like anything. So if I take a quick pick at how a LLM server looks like, a very academic small grade server looks like. We have LLM workload, training framework, collective communication libraries, driver, etc. So here each node will have a CPU and multiple GPUs, which will be connected to another node with again one CPU and another GPU, and both the nodes are connected to each other using network interface card. So here one thing that is intuitive to our mind is that even if I try to increase the performance of a single GPU, it's not going to help me much, because this GPU is going to do a computation. But these lines show the communication. So I also have to think about a better way of communication, both algorithm-wise, data, how should be my interface be designed so that I am minimizing the number of communication, and the communication latency should also reduce. So that was the next trajectory that we saw in the computing, which shows the GPU inference performance. Again on the y-axis years, and on the x-axis I have data operations per second, or the throughput. These are the generations of GPU primarily NVIDIA GPUs, and the name of the generations and the model name, and these numbers basically show the inference. I'll not go these things in detail. I'll just quickly skim through, in the interest of time, what exactly happened. In 2006, we had NVLink. GPU to GPU communication interface actually became very fast. That is the reason we saw 3x speed up. Then, like two different GPUs on different nodes, they started talking to each other using InfiniBand or NV switch, and they also supported the floating point 16. Let's say my workload has just 8 bits data. Why should I waste my resource, which is programmed for supporting 32 bits data, and pad the rest with zeros unnecessarily? So I can fit in more number of F16 bits. That was the tensor core architecture, or the data type that it started supporting, that led to a good improvement of 5x. Then we even went further down to INT8 tensor cores. Even further, the data size reduced, so I can pack in more data, the same amount of resources. And then it started increasing with the tensor core support for the sparse data computation. So all the machine learning workloads are primarily operations, not multiplication, matrix operations. And those matrices are primarily sparse matrices. So once you support the sparse matrix computation, so you can have more throughput or more latency, less latency. So to summarize whatever discussions we had so far, the hardware advancements are important, as well as the software advancement, in order for accelerating the deep learning models. Now comes the concerning part. So here I have plotted from 2010 to 2024 different NVIDIA GPU models with the technology node on which they were built on. We started from 40 nanometer and we are somewhere around 4 nanometer. So what happens with that? The blue bars, which basically shows the performance on the primary y-axis, is increasing. I'm happy about it. But the concerning part is the secondary y-axis, which shows the orange line, the power in watts. So the power here is the thermal design power or the static power. Even when my laptop, let's say, switched on or connected to the supply, I'm not doing any operation, but still it will consume some power because of the leakage current that flows in the circuit. So that has increased at a very dangerously high rate. So the present day GPUs suffer from significant power and energy challenges. The thing is that if it's consuming more power, it's fine. I'm rich, I can pay electricity bills and I can keep consuming that much power, but that's not the case actually. First of all, it's not sustainable. Second, it will have reliability issues. The component next to my GPU chip is going to burn out because of the inductive effect of the heat, because when you are consuming power, you are dissipating a lot of heat. And that is actually when you start giving 1 plus 1 and you start computing it, instead of 2, it will give you 4. Because it's an unreliable circuit, there will be bit flips, many different reliability issues. And then it's also not environment friendly. So what should we do about it? So even the leading AI companies also started thinking in that specific angle, and then this, the obvious thing that comes to our mind, it's consuming a lot of energy because my model size is big, my data set size is big. How can I, how about I reduce that specific data set size? So they also came up with a small language model. So every company started having their own small language model. So for example, Google had Gemini for the large language model. They started launching the Gemma for the small language model, and so on. So the advantages of the small language models are, of course, they're energy efficient. They're also more accessible and affordable. They can be used for educational purposes, cheaper to develop, and so on. The main, one of the main reasons why deep speak from the AI, it has started gaining momentum, that you don't have to buy A100 expensive GPUs. We are academic institutions, we don't have that much resources, so how can we also get a flavor of LLMs, do some experiments on LLM with our commodity GPUs, whatever is in our laptop or so. This attention is basically that figure, where the left side is the encoder, the right side is the decoder figure. And with the emergence of the transformers and their outstanding contribution in the field of natural language processing and the sequence-to-sequence model processing, we see that a lot of companies started having their own LLM tools. And then we are almost thinking about the artificial general intelligence, or AGI, which is a theoretical ML concept where we want the machines to have a human-like intelligence and also have the ability to self-teach itself. And the downside of these massive improvement in performance and throughput is our carbon emission. So we have the AI chatbot, let's say trending app, but it is run on the data center, which will have probably 100K GPUs, and each GPU is consuming a lot of power. So these are some numbers from which I got from the NVIDIA. So the question that we have is like, okay, this energy is also leading to a lot of greenhouse gases emissions, which is also detrimental for our climate, and it might lead to climate change later on. So what should we do about it next? So around 2017, 2018 timeframe when I was doing my PhD, Bitcoin mining got really popular and people started like exploring Bitcoin mining to get rich. So they started acquiring all the GPUs from the market, and that was the time frame when the climate scientists also got a lot of concern, because the GPUs, when they are used day and night, they are also consuming a lot of power, dissipating a lot of heat. So the climate change also became a side effect of the Bitcoin mining marathon. So the next question that we are trying to end our discussion with is, can we reduce the power and energy that is used for the large language models? So if we think about the traditional power management techniques, I'm sure that C-DAC, DRDO have been working on the power management techniques from, I don't know, so many years. So these are the common power management techniques that even I also worked on from the GPU point of view. Is undervolting and power gating. Undervolting means like your manufacturer has given you V maximum and V minimum voltage range. You go below the V minimum, you will not have error instantly, because they also keep in mind some guard band when the temperature fluctuation happens and so on. So that's why they have a buffer. So you're exploiting that buffer to your advantage and still running the experiments. You probably will not have any errors, and in the meantime you're saving a lot of energy, especially the static power which I was talking about in the previous slide. Next is the overclocking, means you are like boosting up the frequency, so which means you will end your application sooner, and the rest of the time you can switch off your circuit, power gating, and you'll save some good amount of energy. And then DBFS. So now the intuitive question that comes to our mind is, okay, I understand these are the power management techniques, but how do I apply in context of LLMs? So LLM has 3 different phases, right? Training, fine-tuning, inference. So which phase is more critical for power consumption? And then second is, like, I also know that there is a computation and communication phase. Computation happens within a GPU, communication happens when I transfer my data from one GPU to another GPU. So the reason communication is also really important is when we are talking about the exaflop machines, our data cannot fit into the memory of a GPU, which is some gigabytes. So I have to divide the data among different GPUs, they do parallel computation, and then they synchronize whatever results they have at the end of the day. So that synchronization is as important as the computation. Sometimes that synchronization or the communication is the main bottleneck for the overall execution time. So which one of them is more energy consuming? So I have 5 more minutes.
Yeah.
Okay. I'll wrap up in next 5 minutes. So in my research group, I started taking a look at the LLM training. So in the LLM training, one thing that we noticed was that the micro-llama model, it has forward pass, backward pass, which is the computation. Then the parameter synchronization, which happens between multiple GPUs or the communication. So one peculiar behavior that we observed was, in the computation, the frequency, the red line is less. These are the computation, the white ones, and the green ones are the communication. The frequency shoots up. I don't know if it's a bug in the application library, whatever, the frequency shoots up like anything. And there is no reason for the frequency of the GPU or the processor to be so high during the communication, because you are not doing any computation at that time. So our research contribution there was, we use the NVIDIA APIs to cap the power. If I cap the power, the frequency cannot go up the ceiling. So we were able to save some energy. So because of the capping, we saw that the frequency dropped, which was high earlier. And if I see the final results, then we do see that like the training time was a little bit high, 1.2%, 1 or 2% longer, but I'm able to save 17% energy, which is a big deal. So now, very quickly, if I see the computation part, so the transformer model takes, like this is a language translation application where I'm taking input in one language, giving the output in another language. It comprises of a bunch of encoder decoder. I'm going to skip through all of this and I'm just going to focus on the self-attention mechanism which made them special. So self-attention mechanism is, let's say I'm taking the sentence, the animal did not cross the street because it was too tired. Now if I ask a human being, what does eat, the pronoun refer to? Does it refer to the animal or does it refer to the street? What will be your answer?
Animal.
Animal, right? So the way machine learns is like it's going to compute, like associate the word eat with all the different words in the sentence and try to assign some weights, and the one with highest weights it will associate with, which is the animal. So this is how it's going to give the self-attention mechanism compute the association of one word with the other words. And this self-attention mechanism is nothing but a bunch of matrix multiplication operations at the end of the day. So making the Amdahl's law, using Amdahl's law, because matrix multiplication is commonly occurring operation, how about we try to optimize the matrix multiplication of the GPUs? So well, I use some traditional machine learning, methods for reducing the power, which was published in some HPC flagship conferences. And yeah, this is the guard band that I was talking about. Every time the manufacturer designs a thing, like the beam also takes into account the guard band, which is because of the difference of temperature, voltage, and process technology. We played around with that, and we reduced the overall time, we reduced the overall power. We had some errors because we reduced the frequency, the voltage below the manufacturer specified limit, and we corrected those faults at the runtime using some fault tolerance techniques. So that was the key takeaway of the research that we have done in the communication as well as computation phase for LLM. And yeah, I'll stop by just focusing on what are my research interests. So I have been working extensively on the GPU performance and energy and sustainable AI aspect, and also have been looking at the SoC. For example, how do you design a domain-specific SoC from scratch? What will be the IP blocks it will have? What are the configuration of those IP blocks and so on? So this is what I was doing in my PhD at UC Riverside, and this is what I have been working on since I started working at Harvard doing my stuff. So yeah, those are the two research areas that are close to my heart, and I'm happy to take any questions.
I have two questions.
Sure.
Quantum talking, is it matrix quantum gates with the algorithm?
I don't know.
Two by two column or row, because see, we're going back end doing these calculations. So is the matrix will control the quantum gate? Gate means I have to get it inside. Does that algorithm allow me?
So we don't know whether we are also living in the simulations. But quantum simulations, because the word is quantum and we simulate in the quantum. So that experiments are going on where can we simulate the quantum phenomenon on a quantum computer. But quantum computer right now we are in NISQ era, noisy intermediate scale computing. And right now we are moving toward fault tolerant. So there is a long way to go whether we can simulate a quantum phenomenon on a quantum computer. That's what we need.
Very interesting.
To just ask you, one is that one slide brought out, billions of parameters. So when LLM is learning, does it treat each piece of data as a parameter, or what are these parameters? That is one. And the second thing, if you could throw some light on, we've been loosely using terms like IPUs, TPUs. So what are these all?
Sure. So the first question is the parameters. So we are talking about each word as a parameter. So depending on we also tell the word as a token in the LLM context. So when we are saying these many million parameters, basically how many words I have in my data set. Second question is the IPU and TPU. So TPU was developed as a, again, domain-specific accelerator for machine learning by the Google. So the GPU part, whichever was contributing to the maximum performance, they kept it, and the rest part they removed it. The best thing in the TPU is the memory mapping, how they can pick the data for the matrix multiplication for computation. It has limited functionality compared to the GPU, but it has way better energy efficiency and performance for machine learning or matrix specific application compared to the GPUs. So that's what CPU is. I'm not sure if that's what you were asking. IPU is again like integer or like the integer processor unit. So again, like all the data that we are dealing with is not floating point essentially, but what happens when I'm like reserving a 32-bit floating point lane for a 8-bit integer operation, I'm unnecessarily wasting the processing power. So how about I try to put in more number of data at the same lane? So that was the integer processing unit that we had. Thanks, but these are two very important questions. Yes.
Let's say yes, GPU can perform the better than CPU.
The data. Could you please repeat
Let's say
the
the single
sentence?
problem cannot be divisible into the smaller parts as smaller
Okay.
problems.
Okay.
On that scenario, GPU can perform better than the CPU.
So if it's not parallelizable, then I should go to the CPU by default because it's good with the sequential tasks. GPU is only good when if I can divide the data and I can utilize all the parallel processors. If I can't divide the data, I can't use the parallel processors. GPU will give me a very bad result. So it's better to stick to the CPU. Any other questions? Yes. Serial networks is. I have not explored a lot in the field of GAN, but my understanding is that it's good with like the neural network prediction kind of tasks. So that's my experience with GANs. I have not gone very deep into the GAN research as of yet.
Thank you, participants, for your questions. Ma'am, please. Yeah, sure.
It is on.
So in view of DeepSeek, which of these slides would you like to change?
Okay, so DeepSeek, right? So whatever they're doing, so in back in the architecture when it was developed, we had big little cores as well. So if you have big tasks, go for big core, or else don't waste the power, go for little core simulations. So I feel DeepSeek is basically how to use the commodity hardware, like let's say multiple little cores, and still attain that accuracy of a big core. So when you are going back to your question, which are the slides that you would like to change? I think the power management technique will still remain the same whether I'm going for a like massive GPU or a small scale GPU as such. But if I had performance slides, I would have to go through a massive DRAM. So performance optimization things, for example, should I prune down my data size or not? Prune down my data types or not? So in the little course, the small data types is anyway supported. So that slides would have to change. For the energy part, I think the concept or the logic primarily remains the same.
No, actually, are you sure? Because the model actually the model size has become much smaller.
Yes.
And also what you said that you have to throw a large amount of data, that also has come down.
So basically the data size, the approximation they have reduced. So let's say if I have instead of 32 bits, I prune down, let's say I have some image processing application. I don't need that much accuracy compared to the financial processing application. So currently anyway they have reducing using the approximate computing and running that parallelly so that I can process two images parallelly instead of one image. So anyway those algorithmic changes are being done, but sometimes what happens when I'm looking at more accuracy and the approximation computing, so when you said model size has reduced, that's because instead of let's say 32-bit, they're processing 8-bit. So if I'm reducing my data type support, anyway like my model size will reduce, the energy consumption will reduce, and all the interlinked parameters are anyway going to reduce.
Actually, all slides will change actually, to my mind.
So, but for example, the DBFS and all those the power management techniques will remain the same. I'll have to look through the algorithm or the application pattern and then have to rethink about it. For example, the frequency behavior that I saw, that was observed for that specific application. If I see what application DeepSeek is taking, I have to see the profiling, and based on that, I'll have to tune down my technique that I'm going to apply.
Thank you so much.
Thank you.
Thank you, ma'am, for your insightful presentation. We greatly appreciate the innovative perspectives. Now, I would like to request Ms. Lakshmi Panath ma'am to felicitate Dr. Devashree Tripathy.